Okay, so my name is Scott Braun. I'm the principal investigator, or lead mission scientist for the campaign. For anybody who's going to spell my name, it's actually spelled with an A-U rather than an O-W. This is HS3, or the Hurricane and Severe Storm Sentinel, is a 5-year campaign with 3 years of science flights, funded as part of NASA's Earth Venture program. It was a program they designed to do big things rather than a single year type of activity, a multi-year activity. We were among the first projects to be selected for that activity. So our main goal is to look at hurricane formation and intensity change. And part of the motivation behind that is that those are really the areas where forecasts still lag. You know, over the last couple of decades, track forecasts have improved quite a bit, but intensity forecasts and what we call genesis forecasts still have lagged behind quite a bit. And so we want to try to better understand what the processes are behind storm formation and intensification. You know, a lot of storms, there are a lot of storms that sort of behave nicely and maybe just ramp up very slowly when intensifying, or maybe weaken slowly over time. So then you get storms like Hurricane Wilma in 2005 that went from a tropical depression to a Category 5 storm in less than a day. And imagine that happening just offshore in the Gulf of Mexico or somewhere else. Presents a very bad situation, obviously, for the public, and a very difficult forecast problem. And it's those types of storms that undergo rapid intensity change that are the biggest contributors to forecast error. So we want to better understand the science behind those processes. And so we're sort of taking a two-pronged approach about doing this. Because the things that control storm track are really just the large-scale environment, basically the winds that are directing the storm, more or less. But for storm intensification, the processes that are important range from those same large scales all the way to the smallest scales. The scales, some would argue, to the individual cloud or raindrops. And when you're dealing with that wide range of scales, it's greater complexity in terms of the processes, much more difficult to measure and understand, and also those smaller scale processes are much more chaotic, and so it's sort of the old butterfly effect that a small change can lead to a very different outcome. So we're trying to get measurements that are on very small scales, also to very large scales. One of the things we're interested in on the large scale is the role of what's called the Saharan air layer, a very hot, dry, dusty air mass that comes off the Sahara with the African disturbances that are often the precursors to hurricanes in the Atlantic. Some have argued that this Saharan air layer actually is helpful or favorable for storm development. It's actually in many ways an energy source for the waves that give rise to tropical disturbances. But many have also argued that they can actually suppress tropical storms and intensification. So we want to address that controversy about whether it's a positive or negative influence. And part of our payload with this aircraft is really geared toward that particular science problem. We're also interested in the role that deep thunderstorms and intense thunderstorms in the inner core of the storms, in the developing eye wall. What role those play in the actual spin up of the storm? Are they the key building block for that development, or are they more of a more symptomatic, an indicator that a storm has energy, but maybe not the main driving force? And that's really the motivation behind the other aircraft. So one aircraft is really looking at the environment and the role that plays in storm formation and intensity change, and the other one is really looking at those smaller scale processes interior to the storm. So on this aircraft, we got 3 instruments. And the very nose of the aircraft is a laser-based instrument. It shoots a laser down toward the surface, and it measures the amount of energy that's scattered back to the instrument. And the types of things that scatter that energy back would be clouds. Particularly what we're interested in are the deeper clouds, so we can see how deep these storms are. But it also can measure energy scattered back by Saharan dust. So it's our main way of sensing where the dust is in the atmosphere, how much, a relative sense of how much dust there is, and tracking that Saharan air in toward the central area of the storm. In the middle of the aircraft, but forward of the wings, is what we call a remote sensor. It measures from a distance the temperature and humidity in the clear air environment, sort of with a coarse resolution, or not a lot of information, but some gross information on where the dry air is, where the warm air is. Very useful because it's continuous in time. And then in the back of the aircraft, you can see that little tube coming out of the bottom of the aircraft. That's our drop-on system. This is the drop-on. So it's a small package, basically the size of a paper towel roll, and inside are some electronics with a GPS transmitter that can tell us, as this is moving with the winds, we can track its location very accurately so that we can determine what the actual wind speed and direction is. And then here on the bottom is an instrument that can measure temperature and humidity, and there's also a small pressure sensor on it. This gives us information, basically a measurement about 10 times a second, I think it is, so that we get very high vertical resolution measurements as it's falling to the surface with this little parachute. So it takes about 20 minutes to fall from the aircraft and gives us very detailed information on what's going on in the environment of the storm. In any single flight, the dispenser that's in the tail of the aircraft can hold up to 88 of these. So we can do up to 88 drops, and basically over the course of the flight really map out the large-scale wind field and where the warm and dry air is. And so this is probably one of our more critical instruments, and the value of this data also is that it's a fairly standard measurement that's been obtained from, for example, the Hurricane Hunter aircraft, but usually from a much lower level. And now we're able to extend those measurements not only all the way through the storm, but above the storm as well. So very unique measurements in that regard. And that information is put onto what's called the Global Telecommunication System, so that the information could be brought into some of the computer forecast models to potentially improve forecasts. Now on the other aircraft, we have this year actually 4 different sensors. One in the nose of the aircraft called a microwave sounder. It basically is geared toward getting similar sort of gross scale measurements of the temperature and humidity in the cloudy regions, and also can give us information of the precipitation within the storm. In the belly of the aircraft, where you see the deep dome, it's called a radome, hanging underneath the plane. There's actually 2 of them on there. The deeper one, forward of the wings, houses a Doppler radar, very similar to what you would see on your evening news, but the evening news radar is standing more or less horizontally to map out precipitation that's moving toward the radar. Here we are looking down in the shape of a cone to map out the 3-dimensional precipitation and wind structure within the raining areas, and then where it's not raining, we're able to get surface wind speed and direction, and that allows us then to connect that thunderstorm activity or the precipitation structure to the overall circulation that we're seeing at the surface, and then connect what's happening in those thunderstorms to the intensification of the storm. And then in the part of the aircraft hanging beneath the tail there is another instrument called a microwave radiometer, and it's geared toward measuring surface wind speed and precipitation. It's in many respects similar to an instrument that flies on a NOAA aircraft, but that instrument only measures wind speed and rainfall right beneath the aircraft, so basically a line following the track of the aircraft. This one scans across the track and can basically give us wind speed measurements over an area about 70 kilometers wide. So in a single pass over the hurricane, we can map out the surface wind speed field. So if we're flying over the eye of the storm, we can basically see the wind speeds in the entire eye wall. And over the course of a flight that may be anywhere from 10 to 18 hours, depending on how far away the storm is from us when we take off, we can perhaps do anywhere from 10 to 20 crossings of the storm, maybe even more crossings of the storm, and map out how that wind speed field is changing over time. So it's a very valuable way of seeing the intensification of the storm at the surface and mapping out that wind field. This year we added a 4th instrument, sort of a piggyback instrument, that's looking at gamma rays emitted by lightning associated with thunderstorms, but it's not one of our core sensors. Now, last year was our first deployment, and we only had this aircraft last year due to technical reasons that I won't get into. So this is our first year with both, and then we'll have another campaign next, our final campaign next year, in what will hopefully prove to be a busier season than what has turned out to be so far this season.
You know,
Bite your tongue. Bite your tongue.
Well, the ideal storm for us is something that forms off Africa. We get it out in the central Atlantic, and then it turns northward out in the Atlantic. Gives us plenty of time. Gives us plenty of time in the storm without it impacting any of the U.S. or any of the Caribbean islands.
Are they pilots here this year, or are they somewhere else?
Say it again.
What's the operator pilots of these?
They're here. We have a set of pilots that operates the aircraft for both takeoff and landings, and then once they're established up in the air, we transfer control to our Dryden Flight Research Center in California, and they do the bulk of the flight. They'll have 2 crews, 2 shifts out there, and then toward the end of the flight, as we're coming back in, they'll hand control back to here for the landings. Pardon? For takeoffs and landing, we have a small T-34 aircraft that will do what's called chase. So they'll be up in the air before we take off and before we land, and then they will follow us from a safe distance to act as the eyes of the pilots to look out for any other low-flying aircraft that ignored the warnings about the fact that we were getting ready to take off. Now, for most of our takeoff and landing, we're in restricted airspace here at Wallops. There's only a very short time that we're actually in the national airspace, and that's why we need chase. So when we take off, we typically are almost immediately into the restricted airspace, and then we go out to the Virginia Capes military airspace, and that's where we go up and then go out to the storms, and we're above all the air traffic.